Alright, time for another drift. Physics.com, debatephysics.com, also video presentation. So, yeah, sort of in the debate news. Not that there's a real debate yet, or a real conversation, but anyway, Bruce Yearney did get back to me. And it was frankly all positive. He's interested, he watches the videos. And he just doesn't have, in his own appraisal, enough physics expertise to be able to compose a clarifying, decisive argument or citation to evidence. But he is thinking about it, and so yeah, that's all good. So maybe we'll get somewhere with that. At least we'll have a advocate, no, a colleague. I don't know what you would call it. Somebody else interested, and somebody who maybe would also like to see some sort of real hard evidence indicating what the truth is. So anyway, that's all good. So we'll see how it goes, how it progresses. So anyway, we're back on photons. And this old video, I think I have played it before, but, you know, as time passes, you know, I'm getting better at understanding exactly their tricks. And they're all tricks. I mean, the more that you think about the little plastic carts they always use that are engineered just for science demonstrations. And I was just thinking about, well, the wheels are metal, which completely unnecessary. It's a low impact cart. And they're really tiny. You know, and the smaller you make the wheel, the faster it rotates. So the faster the axle spins. So, you know, whatever axle there is, or bearings. And so, you know, it's just engineered to put energy into the rotation of the wheelbase, if you want to call it that. And if they used big light wheels, there'd be a lot less energy stored in the rotation of the wheels. It's just a fact. Things, you know, it's Galilean. You know, things roll at different speeds depending on these mass and diameter conditions. So anyway, so yeah, so it is, just looks very canardy. It looks like they're really trying to force the experiments to come out their way, and so they engineer a cart that produces the results they want. And I would argue these experiments with light, they just show you part of the they just show you the part that can prove their thing, and they don't show you the part that, well, indicates something else might be true. So you have to grain of salt, you know, I'm in the grain of salt, saying you got to take this with that and recognize there's more to the story than they're saying. So with that preface, this has all the experiments in it, so that's why this is a good video, because it illustrates how they're very different if you think about it. So they're trying to imply that water is light, is microwaves, is that everything does this. Now it really doesn't. They're very different experiments under very different conditions if you really understand what you're measuring. Alright, so let's play the video. It's playing actually, and there we are. Alright, now you can probably do without all this mush. yes, I could do without it. No, I don't need this in my physics video. Nope. I don't need whatever the hell this is. You could just leave this out and I would be just fine. I would understand the concept. Do.
You now over GC8, heads down on course and on the glide path. Take over, complete your full stop landing. You're clear to Temple, home.
So the mystery of radar. I guess that's what this is supposed to imply.
You've just seen several examples of an electromagnetic disturbance traveling through space.
I don't know what the car driving down the road was, so I guess he was listening to his radio. I don't know. So I didn't get that part.
From a source to a receiver. In this film, we propose to show you that all these disturbances are electromagnetic waves.
Yes, and no, that's not what they're going to show, and they don't even point out that electromagnetic waves, okay, like say if I did make it out of particles, it would look the same. You know, I can just have particles, okay, all launched from one location at the same time. It will look just like a wave. So technically the stuff coming off a nuclear bomb, you could argue, the radiation is waving, the the little bits of people that got blown up is waving, because it's all moving at a consistent speed, okay, in all kinds of different directions. And so any explosion technically could be called waving, but it's really pieces of stuff flying in directions. So, it's just, this is part of the canard, is to try to imply that somehow particles aren't waves. And the same thing really does happen in the ocean, frankly. You have a disturbance in the ocean, there's a bunch of atoms that are going to start moving, jiggling, and they're going to jiggle in a direction, because that's what they're doing, they're moving in a direction. And then each one is going to is going to have a problem getting through the medium. The medium is going to stop the motion, and then the motion has to restart, in the sense that the motion goes in this direction, it hits higher pressure, it has to go up, can't go down into the ground, so it goes up and creates a wave on the surface, and the wave gets pushed down by gravity, the pressure gets pushed back down, and it goes forward again, and that's all it's doing. It's a mechanical system, but they don't show you any of that, and they just keep trying to imply that there's this fake, phony, whatever, electromagnetic ether thingy that somehow is being vibrated by light and other mechanisms. And there is no medium. It's made out of stuff. I mean, you could argue it's a medium in the sense that, yes, the whole universe is full of energy, and you're just changing the frequency of the energy. That is, you're stopping it and restarting it.
We frequently indicate these waves pictorially. Notice the range of wavelengths. Radio waves, about a meter. Microwaves, 1/100 of a meter. Infrared.
So they really don't show the huge giant leaps that these things are in terms of the frequency getting smaller and smaller and smaller, and how gigantic most of those leaps are compared to the tiny leap between infrared and ultraviolet. It's a tiny distance in terms of a frequency change compared to the change from radio waves to visible light. Huge.
About 10 to the minus 5 meters. Visible light, 5 times 10 to the minus 7 meters. Ultraviolet, about 5 times 10 to the minus 8 meters. X-rays, 10 to the minus 10 meters. You have just seen the enormous range in frequency or wavelength over what we call the electromagnetic spectrum.
So it's just the spectrum of frequencies, okay? And the frequency is a real thing in the terms of things oscillate, okay? So it's an explosion that just keeps oscillating, you could argue, or some mechanism of rotation where there's a moon going around a planet. You could argue that the sunlight is being waved, in the sense that, let's say if you reflected light off something, a system like that, there would be a place where the reflection, let's say, and especially if the moon was made out of chromium or something, and it reflected light, you could understand that there would be this blinking, where you get a reflection, no reflection, reflection, no reflection.
You might think that because of this wide variation, that these are different effects.
It's just a periodic mechanism that ends up creating these kind of things, and we produce it. So we send electricity up a wire, and I've gone through this one. Obviously it moves at the speed, almost the speed of light, and what it's doing is creating an impulse, okay, that has a different, tiny little different starting time, And, that ends up being polarization.
Nevertheless, we believe that they are all basically the same. What do we mean by this?
So they are all basically the same. They're all manipulating the same thing. They all move at the same speed. And so all you're saying is that you're changing the periodicity of the event, whatever the event is. And I would argue the event is that there's electrons in the material world, and they're on the outside of atoms, and they're doing this all the time. They're pushing in and retracting out, and pushing in and retracting out. And every time they do that, they change whatever's coming in, just like the reflected moon kind of idea. They change, okay, the reflection of the field of energy that's already in the universe flying around. Your cell phone calls are going to the moon, and they're bouncing off of it at a different frequency than they hit it.
Simply this. If we pick any frequency from the spectrum, we will find the same physical properties demonstrated there as we would at any other part of the spectrum. We're going to...
So what I'll demonstrate is that these different experiments are in fact, though, testing for different things. You're seeing an effect that's being caused by a different event. So some are being caused by you putting a surface in the way and causing a change, and some are just because you're changed positions.
To investigate the electromagnetic spectrum by doing some experiments showing these common properties. Now, what are these properties? First, the transmission from sender to receiver goes as a wave.
So says you. So again, the fact is that laser beams aren't in any sensible way argued to be a wave. In any other sense, then you could just say it's a wave of soldiers. So you could understand that if you send your soldiers in all directions, okay, they go out, okay, at a period, because you send them every 1 second, you send a soldier out to do your battling. Or you could send them out without so much variation. And that's the difference between a laser beam and a regular light bulb, is the laser beam is sending them all out technically or specifically more in one direction than the other directions. And so you're still at the same period, 1 a second, and now you've confined them all to leaving from one location in one direction, one primary direction. No reason to call that a wave.
This means we expect to find familiar wave properties. Secondly, the waves always arise from accelerated charges.
So that's the part they got right. And accelerated charges means this, electrons. So electrons, look, if you can understand that the universe is pressurized in the sense that there's a bunch of radiation flying around in the empty space, a bunch of stuff moving the speed of light. And if you can understand that, then you can understand that every time an electron does this, it's going to interact at a different rate with that medium. So if it's pushing out, it's going to increase the frequency of anything that's coming at it. Okay, that is, it's going to increase the time of the reflection. The reflection happens sooner because the electron was here and now it's here. The reflection has to happen sooner, obviously. And then obviously the retraction is the same thing in reverse, is that I'm going to expand the frequency of events, okay, if I let the reflection happen later. I'm just saying that particle theory doesn't have any problem explaining this. They just aren't interested in explaining it using particles. It is of no interest to them.
Third, these waves always travel in free space with the same velocity.
Which is just a gigantic giveaway that this is something, not nothing. Some things can go the speed of light. Nothings can't go the speed of light. Come on. And why is it all going the same speed? Well, gravity, magnetism, electricity, and light. Why is it all doing the same speed thing? Well, because it's all the same stuff. And all you're doing is changing its configuration. You're changing how it appears.
Speed of light. Fourth, the waves are transverse.
So this transverse crap is just a waste of time. It just means it's moving this way, but it's oscillating this way up and down. It's not really oscillating up and down. So there's no reason. You don't have to believe that. You don't have to think that. It's just coming at a frequency. So there's 1 here, and then there's nothing, and then there's 1, and then there's nothing, and then there's 1. So this makes perfect sense. It makes particle theory make so much more sense if you think about something like radio waves, where at the speed of light, the distance of the wave, okay, could be miles. So there's not some mechanism that's a mile long, okay? There's just a mile between, okay, at the speed of light, the objects, the things that are going to be reflected when they hit a surface or absorbed, the little bits that are flying around in the universe. So it works very well. Particles are very good at explaining that.
By this I mean that the electric vibration is at right angles to the direction in which the wave travels.
Or you could just say there's a period between the events. There's a period of time between the events. I don't need to wave anything. I just say there's a something, then there's nothing, then there's something, then there's nothing, then there's something, then there's nothing. Problem solved. I just have to draw a dot, 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 have the dots moving that way. There, I'm done. I don't need to say the word transverse.
Travels. And finally, that these waves can be polarized.
Right, so the polarization is, again, I could simply draw a Morse code, like dot, 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 have them all on one straight line. Or, as we know from radio, where the impulse has to travel up the antenna, that I send one dot here, going this way, and then I send another dot in this location going that way, and then after another little period of time at the speed of light I send another dot. So we know there's difference. The atoms take up space. The electricity has to go from atom to atom in the sense that it's a transfer of an electron between the atoms, and so obviously the event of the electricity happening to the atom happens periodically as it goes up because it takes time. It's moving a limited speed, the speed of light, or 70 or 80% of it. And that's going to decide the polarization. So the polarization is just the fact that the event takes time, the electricity that's causing the effect. And so because it's atom to atom. One atom does it, the next atom does it, the next atom does it. So the electrons that are doing the pushing happen sequentially. And so you have dot, dot, dot moving the same speed, which is the same thing when it hits a surface. It's still going to be received as, oh, you hit me here, and then you hit me here, and then you hit me here. And you could understand that's just going to reduplicate the electricity in the sense that if the hit means I've accelerated a charge, then I've accelerated it with the first hit. The second hit here is going to accelerate it more, and the third hit here is going to accelerate it even more. Particles have no problem explaining this phenomenon, is the point. Nothing. Not difficult.
And this property is related to the fact that they are transverse.
So obviously, yes. In that sense, you could use the transverse part to just say, okay, it definitely has a shape. It's not just a thin line of Morse code. It's Morse code that happens with two periods. The period between the event and the period between the arrival time. So there's a distance time event, and then there's a time.
We mean when we say that they can be polarized, that we can select any plane containing the direction in which the waves travel.
So that's not a very good description. It can be this way, it can be this way, it can be this way. So it's a frisbee, in a sense. If you understand the frisbee as just being a different sequence of events, it has a shape. So when it lands on a surface as a stimulus, it's going to hit dot, 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 or dot, 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 or dot, dot, dot. It's going to have an identifying extra vector, if you want to call it that.
And can force the electric vibration to lie in that chosen plane.
Just means that when if I was throwing little hunks of polarized light, the fact is it just means that it's making the electricity in different directions. And because metals are crystals, they collect that change in direction in any direction. It ends up being they can only transmit electricity through the crystals.
Now, some of these properties can be determined fairly directly. For example, we can easily measure the speed with which the waves travel. We've done this for you already with visible light. Other properties, such as the wave nature, the fact that these waves arise from accelerated charges, and that they are transverse and can be polarized, must be inferred a little more indirectly.
So again, the fact that charges produce them isn't as much inferred as the other crap, which is just the waves thing. So they shouldn't be making that distinction. They should just recognize that yes, this is a phenomenon caused by electrons substantially. That's you know the electro part.
Doing experiments whose results depend upon these properties. We're going to investigate the wave nature by doing some...
So it keeps, again, it's just push, the wave nature. When again, I could just show you the particle nature, and the diagram is not going to be flawed in any way. I can use the wave of soldier idea and make it perfectly clear that I don't need to think that this is some sort of amorphous wave thing. I can make it out of discrete elements, and it'll look the same. You can turn it into pixels, okay, and the pixels work.
Similar interference experiments in the radio wave region, the microwave region, with visible light, and in the X-ray region of the electromagnetic spectrum.
And they'll be very different experiments, okay? And they'll be claiming it's the same experiment. Well, no, it's really not the same at all.
We've chosen an interference experiment because you are already familiar with this as a wave phenomenon.
So again, more talk, okay? So you're familiar with interference because it only happens, again, in these mediums that don't have their own motion. So we're not really talking about an active system, and you're just using the system like dominoes. So yes, you can create interference in a medium. It happens in atmosphere, sound, because the atmosphere is pressurized. So the atoms are forced into contact with each other. So if you move one atom, you can move 2 atoms, 3 atoms, 4 atoms, because they're forced to be closer than they want to be, frankly.
Along the way, we'll show you that the waves are transverse, that they can...
Water, again, is another example that transmits waves because the water molecules themselves, the atoms, are stuck to each other. They stick. And so that's the glue that makes one move another, move another, move another.
Can be polarized, and that they arise from accelerated charges. We'll start first with visible light. You're already familiar with this as a wave phenomenon.
So again, more talk, okay, about how well we've propagandized and we've stunted it, and we've forced you to believe, and in every way possible, we've tried to narrow the conversation. So again, understood that they won't show you this diagram just pretty much just seals the deal for this whole conversation, because you can understand that this is just about point sources. Their own math concedes it, and it has nothing to do with any waves per se. So anyway, the single slit produces a distinctive pattern that has a double maxima. The nodes are always a little less than twice what's in the center, and less than twice, yeah, a little, one less than twice. So if the node was 3 inches long, the center would be 5, sorry. There's overlapping, is the simple argument. All right, well anyway, and the double slit experiment does the same thing. It produces the same single slit pattern, and it just does it with these little things inside, and that's merely because if this slit dimension is the same for both experiments, that is, the opening is the same size, then this envelope pattern will be the same size. And what you've really changed is this outside dimension. When you move two single slits into each other, what you've created is this distance between the two outside surfaces, and that's the distance that'll tell you mathematically the answer. So it's just so obvious. The greater the distance between the point sources, the greater number of places in which there'll be a full wavelength of difference in the geometry. And so all you're really saying is that I can just figure out how many wavelengths fit in the base of this triangle, and it'll tell me exactly how many nodes I can have going from 90 degrees to 0 degrees. And so I just double it. So if this total distance is 20 or 50, or let's say just 100 wavelengths of whatever I'm putting through, then I'll have 200 spots where there's a difference in the intensity across the entire 180 degrees. Now, how many I see, okay, is really dependent, because the fact is these things always trail off. They, unlike waves, they lose energy. So a huge argument against this being a wave phenomenon is the fact that waves say it should be just as intense at 3 degrees as it is at 10 degrees as it is at the 90 degrees. And it doesn't look anything like that. It looks very intense at 90 degrees and quickly diminishes to nothing. So the whole thing, again, is very mechanical, very easy to understand if you just understand it, fairly. Always an odd number with a double slit in here. So that's a key thing to understand. Right in here, it's always an odd number. And that's what you're going to see here. So let's go back to the video. But it's a simple, it's just about point sources. So the point is the surface creates all the fringe light. So all of these fringes are being created by these surfaces, the photons that go by the surfaces, the fringe light. And the light that goes through the slit, that's why the center is so bright. So if I do a single open slit, I get an insanely bright center, because most of the light just goes straight through. And if I use an impediment, which will give me the same pattern, so I could just make this a block, and the light goes around the block, I'll get the same pattern, but the key will be is I'll have a lot duller center, because I blocked the light going through the middle, and the fringes are still going to be created at the same location. The surfaces are still at the same location, so the pattern will have the same dimensions, and the light that would bleed out the pattern has to come from the further and further outside, which means it's dimmer and dimmer light. So and in some sense the pattern is even more distinct with a single needle or a single impediment, because it's really just about the two surfaces. So the double slit is the 4 surface experiment, and the single slit is the 2 surface. In the double slit, you can understand you really have 2 primary sources. You have this outside dimension, and then you have this small dimension. So the inside dimension is a small dimension, The outside dimension, very big dimension. The outside dimensions, the outside two surfaces are creating the little bars. The inside are creating the envelope pattern. And the little dead spots mean only one source got there. So these are locations only one source hit. The places where there's an off between the envelope pattern. That's just the spot where it's not in phase. So when all four sources are in phase, you have a bright dot. When only two sources are in phase, you got this empty spot, or the empty spot between the dots. Really easy to understand in hindsight. Play.
But before I do the interference experiment, let me show you that visible light arises from accelerated charges. This room houses the MIT synchrotron. Usually when...
So this is kind of also bullshit. In the sense that certainly there's charges in the synchrotron, okay, so, and, you know, but it's a very complex device, and the electrons are being moved by manipulation of the field energy. So that's what you're really showing is that if I have a whole bunch of field energy and then I have moving electrons, I'm going to create all kinds of frequencies. And that's what the cyclotron really shows. It's not only creating visible light, it's creating X-rays and it's creating infrared. So it's creating the entire spectrum. It's probably also leaking a ton of radio waves. So it's not a very good example because he's just focusing on it creating some visible photons, but it's creating, the thing is full of radiation, all kinds of radiation. All right, so the point being is that this machine is basically just creating electrical potentials, huge ones. So things that under normal conditions with an atmosphere would create a huge spark gap. And so they're really just changing how the electrons move from one side of the potential to the other. And you would obviously understand that it's really no difference than saying lightning creates photons. Electrical disturbances creates photons because it changes where the electrons are positioned. And every time you move an electron, you perturbate the reflected energy that's going to come off that surface. So if I have a surface that's wobbling, it's obviously going to reflect irregularly based on the wobble of the surface. I mean, it's really that simple, and he's using this insanely complex machinery to show something really simple. This is just lightning creating photons. And he's making it look like, you know, it needs to have, you need a cyclotron to see it. You don't need a cyclotron. I gotta hit this button.
When we observe visible light, we do not see the details of how light is produced. This is because the light is ordinarily emitted by charges whose motions are on an atomic scale and too small to see. However,
this is still an atomic scale. You still have to produce the electrons with an electron gun. You're just manipulating the electrons once they're liberated.
There's one example in which visible light is emitted by charges moving on a large scale, where we do understand the detailed motion of the charges.
So I'd argue I'm not too sure they do, but frankly, whatever.
This occurs in the high-energy electron accelerators used in nuclear physics.
And again, they produce photons throughout the whole range, not just visible photons. So there's all kinds of energy leaking out of the machine.
Behind all this hardware is a large, circular, highly evacuated tube, which looks like a donut, and in which electrons travel in circular orbits with very high speed.
Right, and they don't travel, they're pushed. So again, push-averse, they're pushed.
Large magnets are used to deflect the electron paths into circular orbits within the donut.
So they're not orbiting, they're being pushed. So they're constantly pushed. Well, pushed through every half cycle around the cyclotron.
If you could look inside the synchrotron, the donut would look something like this. You recall?
So really, this is a huge distraction when you're trying to make your wave theory. There's nothing in this that demonstrates you must have. This is particle physics, obviously. It's not a whole lot of waving going on.
From work on circular motion that a change in the direction of motion implies a radial acceleration, a centripetal acceleration. Now, if accelerated charges radiate electromagnetic waves, we expect that the centripetal acceleration of electrons in the synchrotron will result in the emission of electromagnetic radiation.
And that's constant, and it has nothing to do with centrifugal motion. That is, they're trying to push it into narrower rings, okay, to get the speed of the electrons higher and higher. And so it doesn't have anything to do. It's going to produce these photons regardless of whether you're moving it in or moving it out. It happens all the time.
In this case, light. There is a porthole in the donut which allows us to look at the radiated light.
It allows you to see, okay, visible photons, but there's also a bunch of other radiation, okay, that they're blocking, obviously, so they don't get cancer.
You are now looking through the actual porthole at the radiated light. The light flickers because the electrons are injected into the machine in short bursts.
So it's just seeing a spark gap. There's nothing there, okay? They're just saying, I turned on the electricity, turned it off, turned it on, turned it off, and you can just basically say, oh, okay, that's the spark from you turning it on and off.
The important point, however, is that the light arises from the electrons undergoing a high acceleration as they move in their large-scale orbits. Accelerated charges are emitting electromagnetic waves.
So I'd say that it's a real reach to say that experiment is very enlightening, or more enlightening than a lightning bolt. It's not any more, doesn't give you any more information than just watching a spark in atmosphere.
Here's the apparatus we'll use for the visible light interference experiment. This is a carbon arc source of visible light. The light travels through these condensing lenses and onto a slit here. This slit becomes a single source of electromagnetic waves which travel across here to a double slit.
So this is the really old style way of doing the experiment, where first you had to cumulate the light. That is, you have to try to make the light as parallel as possible. So you're trying to make it into laser beam style light. And that's what the first slit is for, is to eliminate light that's going in a direction, okay, this way, and try to get all the light to be going just in one direction. And then they're throwing it on this double slit.
Reaching each of the slits in the same time. Each of these slits now becomes a new source of electromagnetic...
So the slits aren't the source. The surfaces are the source. That's what the mathematics proves. Their math is just saying, what's the distance between this headlight and this headlight? And those are the sources. Those are the vectors you're going to draw to find your wavelength of difference, to call it your constructive and your destructive, which really just means in phase, out of phase. So again, if I have Morse code ... and then I have wait a little while ... at a different timing, those things can't be received as ... because it's ... that kind of obvious.
Waves with crests leaving the slits simultaneously. These waves radiate out into...
So that doesn't happen. There's not two waves. If you use two waves coming out of the double slit, you're only going to get a single slit pattern. You're not going to get a double slit pattern.
Space in a roughly spherical manner.
So none of that happens. Okay, there's no waves. There's little bits of photon flying off of those two surfaces. Okay, that's the light that's been deflected. So Again, if you could understand, a surface is not a flat thing. It's not. It's made out of electrons. And the electrons are, you could sort of obviously understand, because of the pressure inside the material, the electrons are moving in and out. They're doing this, okay, on the surface. Your photons are coming in this way. They're traveling through, some of them have to travel through that field of electrons wobbling. Some of the electrons are going that way, some of the electrons are going that way. So what happens is basically the photon, the pieces of a photon, are going to fly off going that way, and some of them are going to fly off going that way. And now you're just going to say, well, what's going to happen where they end up? Because they're spreading now. They're going to end up with a big thing on the wall. And there's a 50-50 chance that they're going in phase or out of phase by dimensions, by the math. So yes, half of them become visible photons, half of them become invisible photons, invisible pieces.
Eventually begin to overlap. Where the
So this is such a, a canard, in the sense that they're not really showing you the whole pattern. So you could understand this is the inside of the central maxima. So that's the trick here. So whenever they show you that pattern, and sometimes it has 5 bars. I think later there's one with just 5. But if you count them, this is going to be an odd number. Obviously it starts with 1 in the center, so you can understand it has to be an odd number if it's symmetrical. And so this is exactly this right here, this center. So what they've done is they're not showing you the rest of the pattern. There's more pattern here. There's the second node and the third node, and the other nodes are there. They're just not showing them to you. They're just showing you this central maxima. So they've cut it off and just focused on the center piece. And so they're just showing you the wide surface contributions, in the sense of those are the only dots you can see, and you're not seeing the envelope pattern. But it's there. They're just not showing it to you. They haven't expanded the field of view so you can see the whole pattern. Deceptive. That's where it gets deceptive. So that's an odd number. Always will be. Because it's a center. It's the little nodes inside a central maxima. Always an odd number.
overlap occurs, we see an interference pattern. We get a light region where a crest from one slit meets a crest from the other.
So that's not what's happening. It's in phase, out of phase, in phase, out of phase. And the simple argument is you're making, all four surfaces are making a contribution where it's bright, and only two of the surfaces are making a contribution where it's dark. And you can see the darks aren't as black as the outside surface. So if you really look at the pattern, you'll see that this is really dark. This is gray. So, if you're fair to the experiment, you'll understand this isn't a black line. These are gray lines, not black lines.
In other words, where we have constructive interference, and we get a dark region.
So you could argue the whole, the small surfaces in this case are spreading light evenly across this whole surface. So the small dimension, those two sources are saying make that whole thing a bright. And the outside dimension, the furthest away two surfaces, are the ones making the little lines on top of it and saying, I'll make a contribution. I'll add some extra photons here. I'll add some extra photons here. But it's already a bright, and it's just making it twice as bright. It actually comes out to be 4 times because of the laws of probability, but whatever.
Where a crest from one slit meets a trough from the other, or where we have destructive interference.
So you don't have to believe any of that stuff. You just have an in phase and an out of phase. That's the math, that's the geometry, that's what you're actually measuring is phase. So why they have to keep saying these words interference, it's of no value. And it'll be learned later when you do these experiments that you can completely eliminate the photons traversing across each other's path. So there's no possibility of interference because the photons never cross each other. They never interact. So it clearly isn't anything to do with anything called interference, and it just has to do with you've thrown a signal and it's out of phase, and a signal over here it's in phase, and you can see the in phase and you can't see the out of phase.
We can show that both slits are involved by closing one of them up and seeing what happens. The pattern of light and dark bands disappears, leaving us with only the diffraction pattern of a single slit.
So he called it the diffraction pattern, but you know that a single slit creates bars, right? So where's the rest of the bars? Clearly, again, they've screened the pattern to eliminate all the fringes. So they're just showing you the central maxima. That's it. They're not showing you the whole pattern. You know a single slit creates a pattern. So, I mean, everybody knows that who's seen any of these videos. You know a single slit creates multiple fringes. So you know something's up here. Where's the rest of the fringes? I can only create a blob like this if I have zero different distance almost. You have to have some. As soon as I have a few wavelengths of light, I'm going to start getting a pattern. So there's something wrong here.
So it must be that both slits are simultaneously sending out interfering waves.
So it doesn't must be at all. They never even consider. They don't want to believe in photons. They don't want to believe in particle physics. And so they're just supporting one theory by just saying nobody else has ever said anything meaningful on this subject. Even though lots of people have said something. They can just say it. It doesn't mean anything. Of course, you can explain it with particles.
Before I can show you that we can polarize visible light, we must first understand what this means. Let me get rid of some of this equipment.
Maybe you should have done that ahead of time.
When we say we can polarize visible light, we mean that we can force the electric vibrations of all the waves to lie in any chosen plane containing their direction of motion.
So it's not really true. So a filter is by definition a filter. That is, you filter this way or you filter this way, but all the light doesn't go through the filter. So the fact is a polarizing film this way does block half the light, so to speak. It converts half the light into something you can't see. All right. But anyway, continuing.
Now, if light is transverse, that is, if the electric vibration is at right angles to the direction of motion, then what we need to accomplish this is to have a preferred axis in a plane across the direction of the light beam, such that this preferred axis selects those waves whose electric vibrations are parallel to the axis.
So it's not going to be perfectly parallel. It's in a range of acceptable. That's how it really works. So it's almost vertical versus almost horizontal, that kind of thing.
We have such a device in this Polaroid filter. As you can see, light is getting through the filter.
All right, so I don't want to go into any depth on this subject, but a polarizing filter, you can find out doing the research, is really just layers. So they have a layer that's consistent, and then they stripe that layer with a second layer. So the second layer is, there's a layer, there's no layer, there's a second layer, there's no second layer, there's a second layer, there's no second layer. And what the layers are doing is changing the phase of the photon. So with each layer, you have a phase shift. Okay, so you're changing where that little dot is in space because it didn't progress as far. The phase change is being caused by the fact that when photons have to travel through a medium, a substance, they're going to not get through that substance at the speed of light. Their speed will be changed. And if you change their speed enough, you're going to change their frequency, and you can have like a full wavelength of change, and then it won't change anything because it's still in phase. Or you can have a half wavelength of change where you've changed everything because now it's not in phase. So really, these polarizing filters are changing the phase of the light. So again, it's not really that they're changing the polarization, they're changing the phase.
What has happened is that the electric vibrations that get through are lined up with the axis of the Polaroid. I have another identical...
So he said the words, the ones that get through. Now when he says get through, that implies that half the light isn't getting through, when actually it is getting through, it's just out of phase. So again, there's no heat in the polarizing film. It isn't getting melting or something. It's not absorbing the photons. It's changing their phase. It's just changing where they are in space. They're still going through. Some have been set in time into the wrong location and now can't make a coherent photon.
Identical Polaroid filter, which I'll put in front of this one. And I have previously arranged the two axes so that they are parallel. Light is getting through both of them.
So once you have them in, once you've created a direction, then the next filter won't disturb those photons because they're all traveling in the right line to get through the second grading. But the problem with that theory is too that it's actually the opposite, in the sense that you're not throwing frisbees through the bars of a jail cell. The bars are going this way and the frisbees going this way. You're not throwing frisbees this way through bars going this way. You're throwing frisbees this way through bars going this way. And so the trick is that what you're really doing is taking light and you're going to diffract a little bit of it because of you've put surfaces in the experiment. So you're going to create a little tiny bit of fringing, and the fringing going this way. So for a photon that's polarized this way, a little bit of fringing up and down that is making this polarization longer doesn't do as much damage as if you put a photon that way and that way. You can understand that if I have something lined up this way and I make it go this way or down, that I haven't changed it much. It's still a line this way. But if I take a line this way and I send pieces of it this way and that way, well, now I'm in trouble because I'm going to have a hard time putting that back into a line again.
Now, if I rotate the second axis by 90 degrees, I should expect to get much less intensity getting through to the screen. This is because the vibrations lined up with the first axis reach the second Polaroid and find there an axis at right angles to them. And therefore...
So it's sort of implying that this is what breaks the photons being opposite, and that's not what breaks them.
They should not get
That's
through.
what they get through.
Let me rotate it and see what happens.
The microwave experiment will prove that, because in microwaves you can see the polarizing filter. You can see which way it's aligned. So you'll see that the filter that allows the photon to get through is perpendicular to the polarization of the photon. So the polarization of the photon's this way, the polarization of the filter is this way, and that's the filter it gets through. Because it's only changing up and down in the direction of the photon's polarization. It's not breaking, quote unquote, the orientation of the polarization.
The intensity has gone down. If I rotate it another 90 degrees, the intensity has gone up again.
So again, this always implies that they're blocking light. There's no light isn't being blocked. It's not being absorbed. They're translucent filters, and all they're doing is changing the period of the bits, and by changing their period, changing whether they're in phase or out of phase, and whether they're a coherent pattern. So the photon is a strict coherent pattern, dot, dot, dot. It can't be dot, 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 or dot, dot, dot. It has to be dot, dot, dot.
And this is what we expect, because now the vibrations lined up by the first Polaroid again meet a parallel axis and therefore get through.
So it really isn't parallel. So that's just wrong. The axis of the Polaroid is actually perpendicular.
Now, it certainly can't be that most of the light is a longitudinal wave. That is, that the vibration lies along the direction of motion. Because if this were so, then the axis of the Polaroid would always be at right angles to the vibration, even when I rotate it. And so no one angle could make any difference, and the intensity should not be affected.
So he's trying to imply, okay, but again, the simple argument is this isn't a polarizing film. This is changing the phase. This is a phase disruptor, okay? So it's not really screening for polarization. It's really causing a phase change. And yes, indirectly, that'll allow you to see polarization, but you're really affecting the phase change.
So it must be that light is mostly transverse.
So, no, you don't have to draw that conclusion at all.
And if we wanted to make the experiment more elaborate and could use a better Polaroid filter, I could show you that light is entirely transverse.
Dream on. But whatever. The key point is that he could stick another filter in diagonally. So he can turn off all the light, block all the light, and then he can stick another filter between those two filters, and a third of the light comes back on again. So indicating that the photons are not stuck in the first filter, and they're not stuck in the second filter. They're just broken. So it's a clear example that all you've done is disrupt the photons, and you can fix them. You can put a fixer in to put them back in phase.
I hope by this simple experiment that you now see that light can be polarized, that it is transverse, and that these two properties are closely related.
So again, the transverse part, it's like I said, you don't need to think of any kind of oscillating in any other direction except the frequency. And the frequency is going in the same direction as the motion. So there's absolutely no necessity to play with the word transverse.
Let's do an interference experiment in the X-ray region now.
So this, okay, again, they'll imply that this has something to do with two slits and all that. No, it doesn't have anything to do with two slits. All right, as a premise, it could be argued that, look, the speed of the electron is how fast the frequency would be, how high the frequency would be. So you need an electron that can vibrate. And you're not shooting electrons off of surfaces, you're just vibrating them in and out of a surface. So you can understand, to produce an X-ray, you have to have a very high frequency electron, because what the electron is basically going to do is the infrared radiation is already hitting the surface, and all the electron is going to do is add. It's going to compress that infrared frequency into a much higher frequency by going very quickly into the frequency and compressing it. So you need a very fast electron, an electron that jerks very rapidly a very small distance versus electrons that move big distances slowly. So basically, to make an X-ray, you have to take electrons the energy vibrating off an electron, or the electron themselves, hit a surface where the atoms are of a particular kind, where the electrons can do that little tiny motion. They're under so much pressure that they can move that very quick speed. They can go out very quick and in very quick. I don't need to pause. I need to hit the play button.
This is a typical X-ray tube. It has a very simple structure. This is a glass envelope which is evacuated when in use. There is a cathode at one end which emits electrons when heated. And at the other end, there is a copper plate or anode. A large positive voltage is put between plate and cathode.
So I understand they heat the cathode and then put an electrical potential across it, so the electrons will fly across. So they loosen the electrons with the heat and then push them with the voltage,
thus accelerating the electrons to the anode. When they arrive, they have a very high energy and collide with the anode. This violent deceleration causes the emission of electromagnetic waves. We call these waves X-rays.
Now, it requires you to put a piece of tungsten or some other metal so it evaporates. So it can produce X-rays. So you won't do it very efficiently with any substance. You really need to use specific substances if you're going to get a lot of X-rays out. The X-rays aren't that easy to produce. That's why they aren't just flying out of the sun or coming out of other things. Is because they're not that easy to produce.
This is the apparatus we'll use for our X-ray interference experiment. There's an X-ray tube similar to the one you just saw in this metal can. The X-rays leave the tube here and strike a lithium fluoride crystal.
So again, it's a crystal which just has layers. So they're basically just saying, look, we're going to shoot X-rays. Some of the X-rays are going to bounce off the first surface. Some are going to bounce off the second. Some the third. Some the fourth. That's just changing the timing again. Obviously, you change the timing, you change the phase.
The crystal looks like this and consists simply of lithium and fluorine ions in a regular cubic array. If you looked at the crystal end on, it would look something like this. The important idea to get from looking at this model is that the ions can be considered as lying in planes. And in our experiment, we are going to consider the reflection of electromagnetic waves from these planes of ions.
So you're really just saying where you're going to hit the surface and the X-ray is going to bounce off the surface. So, and the surface is going to be an electron. So the odds of hitting one in the first layer might be 10%. The second layer, 10. You just have a percentage of how deep the X-rays will go, and on what layer they'll finally hit an electron. So, because of the spacing between the nucleus and the shell of the electrons, obviously there's a great deal of empty space that the X-ray can travel through. So it can go hit many different layers. And again, each layers means you've gone further distance, which means your reflection is going to be in a different phase. So it's just another way of changing the phase of the energy.
By using the ripple tank, we can show how this reflection works. Each peg represents a row of ions in the crystal.
So this isn't totally bogus, but I mean, again, you got to understand there's no medium involved here. This isn't exactly the same experiment, but the fact is it does clearly demonstrate that all you're just saying here is I'm just changing the phase, and I'm going to add phases and subtract phases. But there's not going to be anything called true interference. There's not going to really be any signal plus signal equals no signal.
Water waves will be generated moving towards the model. The incoming wave will successively reach each of the planes. Now, the angle at which the wave enters the crystal is important. If the incoming wave makes an angle with the plane, such that the re-radiated waves add up, crest on crest, then we get a strong reflected wave or constructive interference.
Right, so it just depends. This angle depends on what the frequency is going in. So you change the frequency going in, you have to change the angle at which you're coming out, because you're just trying to force the phase change. And so, not much else to this.
And that's just what we have now. Notice that there is a distinct reflected wave leaving the model at the lower right of the screen. The condition for constructive interference involves the angle between the incoming wave and the crystal planes.
So he's calling it constructive, and maybe he won't play with this destructive word. But the idea is just that simple. You're just saying, where have I not broken the phase and where have I broken the phase? So they stay in phase if the period is the same, in the sense that I've moved it a full wavelength. When I move something a full wavelength, a full frequency, so when I change the frequency, the object, and I just move it to the same location where the second node would be or the third node would be, then yes, they all add up, they're all still in phase. And if I do the opposite, then it's not going to work, obviously. Alright, so let's finish up this segment anyway. X-rays.
Only at the correct angle will we get constructive interference. We are at this angle now, so let's mark the angle as a reference. If we change the angle...
If you change the angle, you change the diagonal distance between the different atoms, therefore changing the phase by a different amount. So at the right angle, it's all changed the same amount, so you have the same consistent phase change, and it's all stays in phase. And that's the key point. If the distances are irregular between each one of the pegs hitting at this rate at which the frequency is coming in, then they'll be all scattered in terms of their phases. Yes.
Like this, the individual reflections mutually cancel, and we get a very weak reflected wave.
You get a bunch of scatter.
In our X-ray
Whoops.
experiment, we will be able to detect constructive interference with the lithium fluoride crystal.
My mistake there.
We can see the entire experiment on this diagram. The electron beam in the X-ray tube hits the anode, and X-rays are emitted. They strike the crystal at an angle theta, leave at the same angle, and enter a Geiger counter detector. The output of the Geiger counter is put on an electronic counter.
What if your smile could go from looking like
crap.
this?
Ugh, commercials.
Do in this experiment is to vary the angle theta and look for those special angles where we get constructive interference of the reflected waves.
So you're just saying that we've kept them in phase, and that's all they're saying. So this is really very uninteresting, but let's try to get through it.
Now let's do the experiment. As I turn this dial, I'm varying the angle theta between the incoming waves in the crystal and between the outgoing waves and the crystal. Notice both the lights on the electronic counter and the clicks. We get a click every 64 counts. The intensity is increasing, and I'll stop at a peak. This corresponds to constructive interference between the reflected waves. As I move off the peak, the intensity drops down. And I'll continue to vary the angle. Now we're coming to a second peak, and I'll stop at its maximum. Notice that we're getting interference phenomena, which, as you know, are characteristic of wave motion. We're going to do a microwave experiment now, which will be...
Okay, so that'll be much more interesting, but you'll have to wait till the next video for that. Alright, so I'm just saying there wasn't much to that. You could draw it better than you can actually see it, so blah 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 blah. And if they actually were to draw the geometric lines, you'd see that all you're doing is changing the phase of the reflections. The reflections are either in phase or out of phase. No interference required. Alright, so till the next time, part 2, blah blah blah, and such.